For over a century, researchers have been entranced by the idea of dark openings. This thought started acquiring huge consideration in 1916. These heavenly irregularities remain some of the most fascinating and mysterious phenomena we've discovered, dwelling at the intersection of tremendous gravitational forces and an elusive nature that defies our understanding. A dark opening, which might actually have a mass between 2 to 4 million times that of our Sun, endures as a confounding component in the universe. Even after years of focused research, our knowledge has grown from nearly nothing to gradually accumulating more details, with new breakthroughs continuing to emerge. A recent discovery by Michio Kaku has introduced stunning revelations about the interiors of dark openings, which might challenge established beliefs and present new perspectives on these enormous objects. This new information opens up pathways for deeper exploration into previously neglected aspects. Join us as we delve further into the compelling universe of dark openings and uncover what may be hidden in the vast cosmos. Before diving into Kaku's latest findings, it is essential to revisit what we already know about dark openings. Although most people have a basic understanding of them, key elements remain unclear. In 1916, Albert Einstein's groundbreaking general theory of relativity predicted the existence of dark openings. At that time, the idea was purely theoretical. It was only about 50 years later that substantial evidence confirmed dark openings as real entities in space. This confirmation came during the 1960s in studies of the celestial object Cygnus X-1, a bright source of X-rays. Observations showed that these X-rays were not only irregular but were being drawn into a dense, invisible mass. This mass, later identified as a dark opening, completely transformed our perception of the universe. The discovery was groundbreaking, proving that dark openings weren't just speculative but real, elusive objects requiring further study. Following this discovery, scientists worldwide launched collaborative efforts to learn more about dark openings. This led to the realization that the Milky Way alone might contain around 100 million dark openings. However, due to the immense difficulty in detecting them, this estimate remains speculative. While pinpointing dark openings is incredibly difficult, researchers suspect that thousands of these massive bodies are hidden within our galaxy, making it even more crucial to understand their properties. The fundamental concept of gravity. Dark openings exert gravitational forces so extreme that anything entering their vicinity is crushed into a singularity, a point where the very laws of physics break down. In simpler terms, dark openings act like colossal vacuum cleaners, drawing in everything. One of the most frightening aspects of studying dark openings is the possibility of falling into one. As an object approaches the singularity, it would be stretched apart by immense gravitational forces, ultimately being destroyed before complete annihilation occurs. It's best to stay a safe distance away. Despite being scattered throughout the universe, the closest known dark opening is nearly 500 light-years away, still close enough to be a concern. In 2021, scientists achieved a historic milestone by capturing the first clear image of a dark opening, the M87 dark opening. This was made possible after countless nights of capturing and aligning photographs into a unified image. As more data was gathered, researchers discovered that dark openings consist of 3 distinct layers, contrary to the common belief that they are merely cosmic voids. These 3 layers are key to understanding their structure. 1. The event horizon. This marks the boundary beyond which nothing can escape the dark opening. Once something crosses this threshold, it is inevitably drawn in. 2. The photon sphere. A region where light itself is trapped, unable to break free due to the immense gravitational pull. 3. The singularity. A point where all matter is compressed into an infinitely small space, causing the fabric of reality to collapse, and known physics ceases to function. Every dark opening is unique in its characteristics. While they generally follow this 3-layer structure, their behavior can vary greatly. This makes them particularly challenging to study, as traditional scientific methods do not apply. Researchers must study them indirectly by observing emitted radiation or analyzing the surrounding gas and dust. Sending a probe into a dark opening would be futile since anything crossing the event horizon is inevitably pulled toward the singularity and crushed into nothingness. Given this, spending billions of dollars on probes that yield no useful data is not a practical option. Therefore, scientists must study dark openings in 2 dimensions, despite their 3-dimensional nature. The challenge of understanding dark openings. Adding to the complexity of dark opening research is the fact that no 2 dark openings are exactly alike. Studying them requires considering the breakdown of known physics, as dark openings present a scenario where both quantum mechanics and general relativity must be considered. Theories suggest that dark openings are formed when massive stars collapse under their own gravity. As a star burns through its fuel, it can no longer produce enough energy to counteract the inward gravitational pull, leading to the formation of a singularity. To further study dark openings, NASA researchers focused on the center of the M87 galaxy, where they observed a powerful vortex of hydrogen gas spinning at a staggering 1.2 million miles per hour. This gas should have dispersed due to centrifugal forces but instead remained intact, indicating the presence of a massive object at the center, undoubtedly a dark opening. It is believed that this object could have a mass up to 3 billion times that of our Sun. In 1963, New Zealand mathematician Roy P. proposed a significant theory using Einstein's equations to describe rotating dark openings. He suggested that instead of collapsing into a single point as previously thought, a rotating dark opening forms a thin, ring-like structure known as the ergosphere. This rotating disk of matter is crucial for understanding the breakdown of physical laws near dark openings. Royer's model also predicted the existence of an Einstein-Rosen bridge, a theoretical wormhole capable of providing a shortcut through spacetime, potentially connecting distant regions of the universe or even alternate realities. The concept of wormholes. To understand wormholes, we must first grasp Einstein's concept of spacetime. According to his theory, spacetime is a 4-dimensional fabric warped by objects with mass, creating gravitational fields that influence the movement of other objects. Imagine spacetime as a sheet of paper. If you fold it, you create a shortcut between 2 points. This fold represents a wormhole, a potential passage through spacetime that could instantly connect distant locations. While wormholes remain a theoretical concept with no concrete evidence, they are a natural consequence of general relativity. However, wormholes are inherently unstable, meaning they would collapse almost immediately upon formation. Despite this, the idea of wormholes, especially as a possible pathway for space or time travel, has excited physicists. One type, the CR wormhole, named after Royer, could theoretically link 2 distant points in spacetime, potentially even connecting different universes or timelines. However, the idea of using wormholes for interstellar or time travel presents enormous challenges. These wormholes are believed to be highly unstable, and the extreme radiation and forces around them would make safe passage nearly impossible. Critics of Einstein's equations argue that while they effectively explain gravity, they do not account for the quantum forces governing radiation and subatomic particles. To truly understand dark openings and wormholes, a hypothesis that brings together gravity with quantum mechanics is required. This hypothesis, frequently alluded to as the hypothesis of everything, is a pursuit that numerous physicists, including famous scientist Michio Kaku, have been dealing with for quite a long time. One promising contender is superstring theory, which posits that subatomic particles are actually tiny vibrating strings. This theory suggests that these strings form the very fabric of the universe, explaining gravity as well as the phenomena surrounding black holes and wormholes. However, superstring theory also requires the presence of additional dimensions of spacetime, which are so minuscule that they remain imperceptible with current technology. Despite the difficulties in testing superstring theory, its mathematical elegance and coherence make it one of the most compelling ideas in theoretical physics. At the same time, scientists are exploring other approaches that could lead to breakthroughs in understanding black holes. For instance, quantum gravity is another field of research aiming to merge quantum mechanics, which governs subatomic behavior, with general relativity, which explains large-scale phenomena like planets and black holes. By blending these 2 theories, scientists hope to gain clearer insights into how gravity operates at a quantum level and better understand black holes and other cosmic phenomena. The intersection of quantum mechanics and general relativity is particularly significant when studying black holes, as the extreme conditions near their event horizon create an environment where gravity is unimaginably strong. A theory that can account for both quantum and relativistic effects is essential. The interior of a black hole, where the singularity exists, is one of the most enigmatic environments in the universe. The singularity represents a point where space and time are so warped that conventional physics no longer applies. Understanding this requires a theory that can reconcile quantum mechanics and general relativity, leading to the development of ideas like loop quantum gravity and other quantum gravity models. As we continue studying black holes, one thing is clear. The more we learn, the more we realize how much remains unknown. Black holes are not just destructive forces but also places of immense complexity and potential. Whether they serve as gateways to other dimensions, as some theorists suggest, or hold the key to understanding spacetime itself, black holes remain a crucial area of study. As our tools and theories evolve, so too will our understanding of these mysterious objects. One of the most promising recent advancements has been the development of gravitational wave astronomy. Gravitational waves are ripples in spacetime caused by the movement of massive objects, such as the merging of black holes. By detecting and analyzing these waves, scientists can learn about the behavior of black holes and other celestial objects in ways that were previously impossible. The detection of gravitational waves has already provided groundbreaking insights into black hole mergers, and future experiments are likely to reveal even more discoveries. In addition to gravitational wave research, the use of advanced telescopes and imaging techniques is another exciting area of study. The Event Horizon Telescope (EHT), which captured the first-ever image of a black hole in the M87 galaxy, demonstrated how innovative technology can provide new insights into black holes. By combining data from multiple radio telescopes worldwide, the EHT was able to capture an image of the black hole's shadow, giving us a glimpse into one of the universe's most mysterious phenomena. As technology continues to advance, we can expect to observe black holes with even greater precision, uncovering more about their structure, behavior, and role in the universe. The study of black holes is not just about understanding these bizarre objects in isolation. It is also about exploring the fundamental principles of the universe. By studying black holes, we are learning more about the laws that govern spacetime, gravity, and the very nature of reality. In conclusion, the exploration of black holes represents one of the most exciting and challenging areas of modern physics. With each new discovery, we move closer to unraveling the mysteries of these cosmic giants. Whether through gravitational wave analysis, imaging technology, or new theoretical frameworks, black holes continue to captivate both scientists and the public alike. As we delve deeper into these enigmatic entities, we may be on the verge of unlocking some of the greatest secrets of the universe, perhaps even answering questions that have puzzled humanity for centuries. The ongoing investigation into black holes is leading us not only to a deeper understanding of these mysterious objects but also to a greater comprehension of the workings of the universe as a whole. The more we learn, the clearer it becomes that black holes are far more than just cosmic anomalies to be studied in isolation. They represent key pieces of the puzzle that could unlock answers to questions that have perplexed humanity for centuries. The next big frontier in this field of study involves refining our observational techniques and enhancing our theoretical models. Recent advances in gravitational wave astronomy have already made significant progress. By detecting and analyzing gravitational waves, caused by the acceleration of massive objects such as black hole mergers, we can now observe black hole behavior in ways previously unimaginable. The detection of these waves has already provided crucial information, such as insights into the dynamics of black hole collisions, and experts are optimistic that further studies will lead to even more groundbreaking discoveries. Moreover, the development of cutting-edge telescopes and imaging techniques is opening new doors in black hole research. The Event Horizon Telescope (EHT) made history when it captured the first-ever image of a black hole in the M87 galaxy. This achievement, made possible through the collaborative efforts of radio telescopes across the globe, allowed scientists to capture the shadow of a black hole, offering a glimpse into one of the most perplexing and elusive phenomena in the cosmos. As technology continues to advance, we can anticipate even higher resolution images of black holes, providing deeper insights into their structures, behaviors, and their essential role in the larger cosmic framework. In truth, the study of black holes is not just about understanding these objects in isolation. They serve as fundamental laboratories for testing the core laws of physics, particularly the intersection of spacetime, gravity, and quantum mechanics. By studying black holes, we are not only expanding our knowledge of these unique objects but also deepening our understanding of the universe as a whole. These investigations have the potential to lead to revolutionary discoveries that could fundamentally reshape our understanding of the laws governing the cosmos.